All right. Good morning, everyone. How is everyone this morning? Good. All right. So today we're going to go ahead and get started. We're going to be starting off talking a little bit about package development for R and Bioconductor to set things up. So it's going to be kind of a lot of material at once that we'll be covering. In terms of an overview of package development, and then we're going to dive more deeply hands-on into writing some functions in an example package and getting our hands dirty and doing some exercises later on in the afternoon. So all of the slides for today, at least for this morning, you can find on the Google R Drive, on the Google Drive for Advanced R. So I'm going to start off with this first one here, package development. So you should find an R Markdown document and a PDF document and a couple of other things that we'll talk about later. All right, so let's start today talking about R and Bioconductor package development. A couple references that I'll just link you with right now. There is a free textbook called R Packages by Hadley Wickham. That's a useful reference. We won't really use it too much, but I'll reference it in case there's something that I don't cover in sufficient detail and you want more specifics on a particular topic. And of course, there's also Writing R Extensions by the R core team. This is the official, extremely thorough manual written by the R core team members that goes into extreme detail on everything you should need to know about package development. I would definitely start with the first one, and then once you feel sufficiently prepared and need to know how to do something, you can look at Writing R Extensions, which has everything you should ever need to know about that. Okay, so first off, let's talk a little bit about why you might want to build an R package. And ask this to you directly. Who here has built an R package before? Got one, two, three, a few people. What kinds of R packages have you built?
I put one out on the grant for the skeleton distribution, which is a difference of plus on. Pretty much anything that I do that is likely to be reused, I package.
Yeah, I think it's good to, once you find yourself reusing something frequently, that's a really good time to start thinking about putting that together into an R package. Anything else that other people have built? Anything else? What are some reasons that you might want to build an R package? Yes. I'm sorry, speak up. Yeah, so sharing code with collaborators, sharing code with users who would use your package. So obviously I think all of us use some kind of R packages in our daily lives, at least on the work side of our daily lives. So there are lots of reasons that you might want to build an R package. Even if you're not planning on distributing your package, there's a few good reasons to organize your code that way. Is that a question?
It's sort of under documentation, but if I'm going to come back and do the same thing again in 6 months, I have no idea what I did 6 months ago.
Exactly. You may write a function one day, come back to it in 6 months, and have no idea what it was, and having some sort of documentation, whatever that documentation is, really helps. Code comments work, but writing an R package really forces you to be explicit about that documentation. So a few reasons to build an R package lets you easily manage and organize your code, so you have a bunch of R scripts, and putting them into a package gives you something that's a little bit more manageable and easy to work with. Lets you portably reuse your code. So especially if you're submitting to a repository like CRAN or Bioconductor, that means people can use your code on different platforms. So I mainly develop on my Mac here, but people on Windows or Linux or other systems can use my packages without me having to worry about building the binaries for those and all of that. Documentation for your code, we just talked about that. Making dependencies on other packages explicit. So lots of times if you're just sharing R scripts with other people and you want them to run those R scripts, it's kind of difficult to make sure that they have all of the necessary packages installed installed to run those. You might add something at the beginning, install these packages or install packages and just have a list of packages, but that doesn't always capture all of the dependencies, and some of those packages might depend on other packages, and it can be a mess. But having your code in a package simplifies a lot of that, because especially if you have it on CRAN or Bioconductor or some of the other tools that we'll be using today, makes it easy to install all of those packages whenever a user installs your package. And of course, it lets you distribute your code so other people can use your code, possibly extend your code and make something new from it, write new methods for it, create new things from whatever kind of data that you are working with.
It may be my own ignorance, but I don't know any other way to link in C or Fortran than from source.
Well, you can incorporate C and C++. I haven't personally worked with Fortran because I haven't worked with Fortran. I've been fortunate in that way. But at least C and C++, you can incorporate them without writing a package. I think having them in a package is probably the best way to do that, since it makes it a little bit easier. Again, lots of things. Building a package is one of those things that's very hard up front, but it pays off a lot in the end. So let's talk a little bit about a couple of example packages that either you may have used or that we'll kind of look at in terms of big packages on Bioconductor that are relevant to what we'll be doing. So one of those is MSNBase. This is a package by Laurent Gata, who's teaching next door. So this is kind of one of the central R packages on Bioconductor for working with proteomics and mass spectrometry data. If you started off with Bioconductor a while ago, there's a central Bioconductor package called Biobase, and there used to be, I guess there still is, this class called Expression Set and ESET that used to be used for working with microarray data. It's not used as much anymore in favor of the newer summarized experiment class, but MSNBase was kind of originally inspired by writing essentially a proteomics version, a mass spectrometry specific version of the classes found in some of those original Bioconductor packages. A few other packages of note. We have summarized experiment. This is one of the newer core container classes from Bioconductor core. Vincent Carey talked a little bit about summarized experiment the other day. The main idea is it can contain essentially any kind of experiment that has multiple assays, where the rows of this summarized experiment refer to whatever features are in your experiment. Typically, that's going to be genomic ranges for the people who use summarized experiment for genomics, and the columns represent the samples. MSNBase has a similar class called MSN Set and MSN EXP for MSN Experiment. That's more specialized for proteomics and mass spectrometry. And Cardinal, which is my package, is kind of doing a similar thing, but with a focus on mass spectrometry imaging. So each of these are different packages that implement some kind of core classes for working with different kinds of data. And the idea is that people can depend on these packages and create new methods building from the classes of these. So if you want to work with mass spectrometry data in R, you don't need to program everything about mass spectrometry from scratch, because you can go depend on MSNBase, or if you're working with imaging, go depend on Cardinal, and use those core classes, those existing methods for manipulating that kind of data, so you can focus on exactly whatever you need to get done, whether that's developing a new statistical method, integrating with some kind of new workflow that you're doing, whatever that happens to be. So I'm not going to take too long to dwell on this, but just think about what kind of packages you might be interested in writing, either to extend these or to provide some sort of new additional functionality and infrastructure. So I'm going to kind of start out here supposing that you want to write a package for Bioconductor, and maybe you don't. There's lots of other reasons you might want to build a package, but this is going to be kind of the mindset that I'm starting off with. So let's think about what it means to write a package for Bioconductor, everything that entails. Who can tell me the first step? Make a package. So the first step to putting a package on Bioconductor is to make the actual package. How do you create a package? That's something we'll be talking about today. Some other good things to consider when you're submitting to an existing ecosystem like Bioconductor is you typically want to reuse whatever existing infrastructure they have. So for example, for Bioconductor, if you're working with mass spec data, you probably want to use whatever existing infrastructure exists there in MSN-base, or in the case of imaging Cardinal, or in genomics, there's lots of other classes specialized for genomics. So it's typically good to reuse whatever you can, and we'll talk more about classes and methods and some ways to do that. Once you have a package, you need to make sure that package is documented with both manual pages, we'll talk about those, as well as vignettes, so that your users can have a nice walkthrough for common workflows and understand how to use your package. You need to test that package with unit tests. You need to make sure that package passes our command check, and if you're submitting to Bioconductors, it's a package called BioCcheck that performs some additional checks. So these are just things that make sure everything in your package passes the sufficient requirements for a decent package. Then you want to submit it to the Bioconductor, and at that point you enjoy maintaining your new package and fixing all of the bugs that people eventually find. So we'll get started. You should already have these packages. One of these wasn't explicitly in the list, but devtools should install this, use this package automatically, so you should already have that as well. I'm just showing you this here for if you didn't happen to install these packages already. You should already have them, but these are a few helper packages that we'll be using a little bit today to kind of automate some aspects of package development. You can, of course, write an R package without any of these other tools. Absolutely everything you need to build an R package is already provided when you install R. But these are a few packages that help make your life a little bit easier in some places. So devtools is a package that helps essentially with lots of little aspects of building and installing a package from scratch. Use this is a package that used to be part of devtools. It's now its own separate package, and it automates some of the setup and just throwing common infrastructure into the package, like it gives you a directory for unit tests, a directory for RCPP or C code if you're using that. Just automates a few simple setup things. Roxygen 2 is a package that lets you write documentation with structured code comments, rather than writing the LaTeX style documentation by hand. And TestThat is one of the packages that you can use for unit testing. We'll talk more about unit testing probably tomorrow. TestThat is one of the packages you can use for that. There's another one called RUnit as well. Again, I want to emphasize all of these are totally optional. We'll be using some of them, but you don't actually need any of them. All right, so let's start off by creating a very simple package template. So R gives us a couple of ways to kind of get started with a very, very simple bare bones package. Find my RStudio here. Okay, so first I'm going to use the create_package function from the useThis package. So this just creates a package skeleton, as well as creating a new RStudio project for that package. I can just give it the name of whatever I want to name my package. I'm just going to call it package template 1 here. I'm going to double check where I am. My current working directory is kind of low. Let me bring that up a little bit. So my current working directory is this, the copy of this R package development folder on my own computer. So by default, this will create the package in whatever my current working directory is. So I'm just going to call that right now. And you can see, for one thing, it starts off, it creates a new RStudio session with a new RStudio project for that particular package that it just created. I'm going to go over here and see here is the folder that it just created. I go look inside it, I can see a couple things. I see a file named description, a file named namespace. I see another folder, directory called R, and there's also a couple of hidden files that we don't need to worry about right now. And in the case of this particular function, it creates this RStudio project. We haven't really talked much about RStudio projects, but they're just a way that RStudio lets you manage either package development or whatever collection of files that you typically use together as a project. It's not necessary to use it at all, so I'm just going to close out of that. So that's one way to start off with the package skeleton. Now I'm going to use the package.skeleton function from base R. So this one comes with R. It works a similar way, so I'm just going to give it the name of a package that I want to create in my current working directory. I'm going to call it package template 2. You can see it created a few things here. And I have a new folder here called package template 2. I can see some of the same files and folders that the other function created. So I have a description file, a man file, a namespace, an R folder, and a read and delete me help thing. Alright, so let's take a look at a couple of these files. So let me look at this description. Well, that's fairly straightforward. It's a description of what the package is. We'll look more at that later. There's a namespace. We're not sure what that is just yet. And there's an R folder. Probably that's where we're going to put all the R code. So what a package, an R package actually is it's just a directory that has certain requirements for its layout. So the directory layout of an R package is just, you have some sort of folder or directory, that's the package name. You have a description file. This is a structured description of the package. There's a namespace file that we'll talk more about later. This is responsible for managing all of the packages that your package depends on, all of the functions that you want to use from other packages, and also making sure whatever functions or classes you want your users to be able to use, it exports those functions and classes to your users so that they can use those from your package. The R directory, this is just where you'll put all of your R code in however many rscript.r files you like. Man is a folder that will have the documentation for the manual. Source, we didn't have one of these, but if you have C or C++ code, and we'll look at more at that tomorrow, that's where any compiled code lives. There is possibly an inst directory that we didn't see. But this is just where you would put any miscellaneous files. There's a data directory if you happen to include any data in your package in rs.rdata or .rda format. It's a directory for unit tests, a directory for vignettes, and then potentially some sort of news file that gives users a change log of what you've updated in the most recent versions. And some number of these are optional. In other words, that not all packages need all of these to function. Kind of a minimal requirement if you're making an R package, you need at the very least a description file, a namespace. Unless you're writing a data package, you probably want some sort of R code. That's probably why you're making an R package. So you need some sort of R code in your R directory and some sort of documentation in the man folder. R will still build and install a package that has just a description file and an R subdirectory. It doesn't initially complain about missing documentation, but if you actually want CRAN or Bioconductor to accept your package, you absolutely need those. Bioconductor itself has some additional requirements, such as having an introductory vignette describing common workflows in your package and some unit tests. And all of these you can create by hand. You don't need any additional tools, but there are some tools for automation using those packages we talked about a moment ago, and we'll see how to use those. So devtools. DevTools helps with all aspects of building, checking, and installing packages from within R. You don't need DevTools to do any of these things. They just let you do it from within R rather than doing it on the command line. It's kind of a personal preference whether you want to do it that one way versus the other way. It has a function called document that lets you generate Roxygen 2 documentation. Load all kind of simulates loading your package as if for the first time without actually going through the process of building and installing it. Build is for building packages. We'll talk about what that means. Install is for installing packages, and check is for checking packages. Use this. This used to be part of the DevTools package. It's now separate, but this just lets you add some common development infrastructure to your packages. So it has some functions for adding a folder for unit tests, using teststat, adding a template for a vignette, adding a template for adding RCPP code, and also that function we use to just create that general package skeleton in the first place. Roxygen 2, this is inspired by the Doxygen documentation generator for other languages like C++, Java, Python, and so forth. The idea is to generate our documentation from structured code comments. Rather than writing all of the documentation by hand, you still need to write the actual documentation. It just simplifies it a little bit, and you get to write that documentation in code comments that's right next to your code. So in some ways it can be easier. It also automatically generates the namespace file. So it generates what is responsible for importing and exporting functions from your package into the user. And we'll talk more about that. We'll see some examples when we get to looking at our example package. And teststat is one of the R packages that you can use for conveniently writing unit tests. RUnit is the other most popular one, and again, we'll look at that more later. Again, I've emphasized this several times, but everything you need to build an R package comes with R itself. All of these previous mentioned packages are entirely optional. I mostly emphasize that because I personally don't often use them. I know lots of people really like working with these packages. They make lots of people's lives much easier. Personally, I kind of prefer building things from scratch. I sometimes find using too many automation tools like this, managing those can become a chore in itself. So I'll show you how to use these. If they seem like they'll make your life easier, if you like them, please use them. If it gets to the point where you don't like them or they're making your life harder than it seems like it should be, then just don't use them. And please stop me if anyone has any quick questions while I'm going through this. Alright, so how exactly do R packages work anyway? So before we build an R package, let's talk a little bit about how a package gets from the state of this source directory with these R scripts to the point where it's a loaded package that you're working with in R. So a single package can actually exist in 5 different states. You can have the source package, which is the version that we just saw as a directory, several other versions, and eventually the in-memory package, which is the way that is represented when you actually have that package loaded and are working with it in R. Let's talk about each of these individually. Source package, this one's really simple. It's just the directory with that particular file structure. So here, package template, this is just a folder with an R folder, a man folder, a description file, and so forth. This is a source R package. So is this package template 1 folder. They're not very good packages yet, but they are source R packages. This one's fairly simple. Okay, so a bundled package. A bundled package is kind of the next level from a source package. This is a source package that has been bundled and compressed into a single file with the extension .tar.gz. So if you go to CRAN or Bioconductor and you want to actually get the source code for one of those packages, this is typically what you will download. So for example here, I'm looking at the Bioconductor page for MSEnbase. And if I look at the different ways I can get this package, you can see there's a Windows binary, Mac OS binary if I want to install the binary version. But the source package here, this .tar.gz file, this is essentially what I would typically download if I just want access to the source code, if I just want to download the source code. And all this is just, it's essentially a source package that's been compressed. All of the files and directories in the source package are just reduced into a single file using the Unix tar utility, and then compressed using gzip. Lots of people will refer to these as source packages because they are essentially just compressed versions of the source package. And the way that we build these is, if you're using devtools, you can just use the build function on your package. On the command line, the way to do this through the R command line is R command build. So, I'm not sure if this is a good idea or not, but I will build one of these little package templates, even though they don't actually have anything functional in them, but let's try that out. So I'm going to do devtools build package template 1, or build. Not bold, build. So we can see it did a few things. And at the end of the day, I have a bundled package template 1 .tar.gz bundled package. So that's a bundled package. It's essentially just a compressed version of the source one. Now, a binary package is what you will typically initially download from CRAN or Bioconductor when you go to install.packages or BioC manager install. So this is an R package that has been optimized a little bit in terms of allowing you to download it and easily install it. So a binary package, firstly they're Mac or Windows specific, so you can't go take a Mac binary package and install it on Windows, or a Windows binary package and install it on Mac. They don't actually even exist on Linux at all, because Linux likes installing everything from source code. But what a binary package is, all of the R code in the R directory has been parsed, evaluated, and output as saved.rds files for faster loading. I believe the newest versions of R also byte compile them by default. So all of the R code has been changed from just the plain text source code into some sort of binary format that R can easily and quickly load. Any compiled code in the source directory, so any C, C++, Fortran files, and so forth, these have been compiled into the binary executables for their respective operating systems, so either Mac or Windows or Linux. All of the documentation and vignettes have been converted to either HTML or PDF, or don't think there's any other allowed formats. But all the documentation and vignettes have been prepared. And the way that we can build a binary package, you shouldn't ever typically need to build a binary package on your own. Typically, either CRAN or Bioconductor will do that. And if you're not on a repository and just want to give your package to someone, you probably are just going to give them the bundled version. But if you want to build a binary version of your package, you can do that either with devtools build with binary equals true, or use R command install -- build in the command line. So, kind of high-level overview of what happens to all of these different directories when we go from source to bundle to binary. Going from source to binary, pretty much everything remains the same. Main difference is any things that are kind of extra that you don't necessarily need. So if you're submitting to CRAN, you would have an additional file called CRAN comments. The R project, R Studio project that the use this template creator creates. Any of these sort of additional extra files that the package doesn't actually need, these go away when you bundle it. The other directories pretty much stay the same. A couple of them are renamed. And then when you go from bundle to binary, a lot of things happen. Most of it happens with the documentation. Those get split up into the actual documentation files that the installed package will use. The description also gets parsed and changed a little bit so to make it easier for R to read. And all of the R files still stay in an R directory, but they become, usually they'll be byte compiled nowadays, but essentially they'll be put into some kind of binary format. And finally, we get to an installed package. So an installed package is what you actually end up with as a file or folder somewhere on your computer after you've installed a package. So an installed package is actually just a decompressed version of the binary package that has been saved to a package library. And what I mean by a package library, typically you will actually have two package libraries on your computer at any given time. Despite the confusingly named library function, a package and a library are not actually the same things. Library loads a package from a library where you typically have two libraries. One library contains all of the packages that you've downloaded and installed yourself. The other library has all of the R packages that come with R itself. So a library is just a collection of packages that have been installed. And the way we can install a package is either with R command install or install.packages. I imagine this will fail, but let's try devtools install package template 1. Oh, I was able to install this package that does absolutely nothing. R is pretty lenient in what it lets you install. CRAN and Bioconductor are not so lenient. And the way that I could do that from the command line. Can people see that okay? Okay. So the way that I could do that from the command line, so with devtools install, what I just ran, this devtools install works on the source package. The usual way to do this through the command line when I'm using R command install is I typically want to give it the bundled version of that package. So I'm going to give this that bundled version of the package. One tells me that there's no documentation pages, but there is otherwise no problems, which is, I guess, not that surprising since there's no code to find any problems in. So kind of the roadmap of how we get from source to bundled to binary to installed, and then finally in memory packages, which is what you have when you actually load the package. There are a couple ways to do that. If you're installing from CRAN, you'll typically download the binary and install.packages will just go straight to installing them. You can install packages from source on CRAN too every once in a while. Every once in a while I've had to do that when the source package is newer than the binary that they've built. You can do that as well using install.packages. Then you would download the bundle and install.packages would then install it. If you use devtools install, that just operates on the source package itself, and it'll take you straight from the source package to the installed version. DevTools also comes with a nifty little function called install GitHub that lets you install packages from GitHub, and that will take you straight from GitHub to an installed version of that package. And R command install itself, you will typically give that the bundled package, which is what I just did. Any overall general questions so far? All right. And finally, we get to in-memory packages, which are just installed packages that have been loaded in memory during an R session. Something to note is that a package may be loaded into memory but not actually be attached to the search path. So you do not actually need to use library in order to load a package into memory and be able to use it. What library does is actually load the package and also attach it to your search path so you can use the functions and other objects from it without needing to fully specify them. So earlier, I was using functions from DevTools like this. I was using this double colon operator to specify I want to use the build function from the DevTools package, and you can see that I was able to do that just fine, even though I hadn't actually called library on DevTools at any point. And I can see what packages are on my search path by typing search. These are all of the packages, well, in this case, these are all the packages that are loaded by default. But if I did library on something, let's see, what the matrix package. If I did library on a package, that would both load it into memory and also put it on my search path, so I can use the package, use the functions and other objects from it without needing to go through and fully specify which package I want, colon, the name of the function from that. So I can load and use functions from a package just by using a function from that package. So you don't need devtools to be already loaded to do this. As soon as I call a function from devtools, when it's fully specified like this, R will be smart enough to go load devtools into memory and let me use those functions without attaching it to my search path. Alright, so a typical workflow for how we go from a source package to an installed package with our command, so the command line version. So we typically start off by building a bundled version of the package with our command build. Optionally, we should check that package with our command check. We haven't done that yet. Then we can install that bundled package with our command install. Optionally, if you want to build a binary version, you shouldn't typically need to do that, but you could do that with our command install --build. Binary packages are actually built just by compressing the installed version of the package. So what happens when you actually build a binary package, it just first installs it and then compresses the version of that package that it just installed. And then once you have done at least these two, then you can just load the package in R with a library, or just by calling a function from it. DevTools simplifies this process to just 2 steps if you just want to install a package. So DevTools install, as we saw, will just install a package straight from source, and then you can load that package with library. So one question is, why exactly do we need these bundled packages, the .tar.gz version? Especially since DevTools just lets you install directly from the source package. It may not seem totally necessary to build these bundled versions. There's a couple of reasons that we'd want to do that anyway. Firstly, our command check, which is what you would run when you want to make sure you have everything that you need to in the package. Checks your documentation, checks for common problems in your R code, checks your unit tests, all of those things. Our command check should typically be run on the bundled packages. So if you want to run our command check, you should build a bundled version of the package first. In addition, if you want to just give your package to someone else and it's not on CRAN or Bioconductor yet, bundled packages are the easiest way to do that. Unless it's on GitHub, then you can just send them to GitHub. But sometimes you don't have internet access. Questions?
So, on that last comment you made, why these binary packages are a good option?
So binary packages are, question is, why are binary packages not a good option for sharing? And the answer is that they can be if you know that whoever you're giving that package to has the same operating system that you do, and well, that's the most important thing. They have to have the same operating system that you do. They should probably be using a similar version of R and other things like that. There's lots of things that can kind of go wrong when you build a binary package. In most cases, you shouldn't run into problems as long as they have the same operating system. But that is one additional hurdle. In addition, it doesn't give them the source code. So if you want them to actually be able to look at your source code and help you with it, or check for problems, or be able to use that source code in any way, giving them the binary version of the package doesn't help at all. So if you want them to actually have the source code, that's one more reason not to give them the binary package. It's also just, I don't like having to compile things for someone and find out that it didn't work for some reason. Lots of things can go wrong with that. I prefer to just let CRAN or Bioconductor deal with building the binary versions. That help? Any other questions so far? Okay. All right. So, if desired, DevTools automates a lot of these steps. So, our command is the way that we would do most of these steps from the command line, and is typically the way that I personally do it. But DevTools does have these nice functions for letting you do a lot of these things from within R. So DevTools build lets you build the bundled or binary packages. DevTools checks the packages. DevTools install builds and installs the packages all at once. And then DevTools load all. This is probably one of the more useful ones that you can't actually get through R command on its own. Load all is intended for rapid iteration, so when you're building a package and you just want to test out whatever quick changes you made to your code, and you don't want to go through the process of building and reinstalling that package from scratch and starting a whole new R session for all of that. Load all is really useful in that instance, since it lets you just essentially load a new version of your package as if you had built it, installed it, and all of that, and loaded it from scratch in a fresh R session, but without actually having to do that. So it's really nice for that purpose. It does not actually do all of those things, so you shouldn't rely on it as a replacement for those things. It's very useful when you're working on a package and you want to test things and you want to iterate quickly, but it's not actually a replacement for actually building and installing and checking your package. It's just a nice, quick thing that lets you load all of the code from your package as if you had it installed and reloaded and all of that. All right, so I've built an example package that we're going to be working with for the rest of this course. It's called MSExample. You have a bundled version of it in the Google Drive already, but if I can find my Google Drive. So you already have a bundled version of it on Google Drive. You should also go ahead and check the GitHub of it. So if you just follow the link, I'll go back to the slide where that's a little bit clearer. So if you just go to my GitHub, github.com/kuistelu, KUWISTELU/MSExample. Later on, I'll ask you to fork the package to your own GitHub repository and clone it to your computer, so you can work with it a little bit for some of the exercises we'll be doing. You don't need to do that right now if you don't want to, but just take a look at it. So this is a very, very simple R package that we'll be using. To be relevant for this course, it provides a simple workflow for processing raw mass spectra, as well as a function for actually simulating those raw mass spectra. It's not intended for actual use. It looks like it works. The functions are very, very simple, so if you actually try to use it production-wise, I have no promises whatsoever. If you want to process raw mass spectra, and actually you should use a real package like MSNBase or Cardinal or MaldiQuant or one of those other R packages designed for that. This is just to give you, for us to work through some examples in terms of how to build and install packages, how to put together a more complicated package in terms of something with multiple functions, with different S4 classes and methods, which we'll talk about after the break. So let's start off by taking, and we're going to use this package to look at some of the things that go into a package in more detail. So things like the description file, the namespace, the R code directory. So we're going to go ahead and start off by looking at the description file. So this is just a plain text file that lists various aspects of your package. Every single package will need one of these description files, both the use this create package function as well as R's base package.skeleton creates the description file automatically that you will then need to edit. So you can see this is the description file created by R package.skeleton. And all this is just a plain text description of your package. Gives the package name, a title, which is a slightly more descriptive name for your package, a version number, author. So this is you, whoever else authored the package with you, the maintainer, the person that will be bugged whenever it breaks, description, so this is just a longer paragraph description giving a little bit more detail on what your package does. Depends, imports, and suggests. These are the different packages that your code depends on in one way or another. Depends is a list of packages that must be loaded and attached whenever someone loads your package. So whenever someone does library on your package, all of the packages on this depends line will also be loaded and attached so that the user can use them. Imports is the list of packages that must be loaded that your package depends on, but your users don't necessarily need to interact with. So packages that are imported here, your package will have access to them. You can use them in your package, but they aren't automatically attached so that the user won't necessarily have access to those unless they load that package themselves, or attach that package themselves to be specific. Suggests, these are packages that users don't actually need at all, but that your package depends on for things like unit tests, vignettes, conditional examples in documentation, things like that. So things like test that, knitr or R Markdown if you have a vignette in R Markdown. So these are packages that are not needed for your package to function, but your package either is enhanced by them in some way or relies on them in other situations like unit tests or vignettes. Some sort of license often, and here is the description file for this MSExample package that I have on GitHub and that I gave you the bundled version of. So a package, MSExample, type, it's a package. Title, as an example, our package for mass spectrometry. Version, date, author and maintainer is me. Description, a slightly longer paragraph. License, depends, imports, and suggests. Encoding, this is something that Roxygen 2 requires. So there are some additional fields that not all description files will have. In this case, encoding UTF-8 is something that Roxygen 2 requires if you want to use Roxygen 2 to automatically generate documentation based on your code comments. Vignette builder, this is because my vignette is in R Markdown and needs the knitr package to create it. And if you're submitting to Bioconductor, you will also need some BioC views. In this case, I just have mass spectrometry there, but you would have any other relevant BioC views from Bioconductor on that line if you're submitting to Bioconductor. Yeah.
So this like the license and other technical words, for example, the encoding, the imports, those ones you manually put in or the ARM package itself decides on those?
So all of this, well, all of this you can write by hand. If you happen to create a template for your package from package.skeleton or use this create, it'll fill in some of these words for you. But in general, you're responsible for having this all, writing this all yourself. None of this is created automatically, with the exception that you can get a template. But you are responsible for filling in most of these. So like encoding UTF-8, in order for Roxygen to work, I had to put that in myself. Depends, import, suggests, you're responsible for making sure those are correct yourself as well.
And what about the license?
License is whatever you want it to be. I'm not sure if it actually checks if it's a valid existing license or anything. I use Artistic 2, use GPL, whatever license you want. You can optionally include an actual license file. I haven't felt the need to do that. I'm not actually sure if that field is required or not, but considering our packages typically need to be open source in some way, I'm not sure. But yeah, it's just whatever, a name of whatever license you want to use. Any other questions on the description file? Okay, let's talk about the R subdirectory. So this subdirectory just contains all of your R code in .R scripts. You can manage your code essentially however you like. So you can have one huge R script with absolutely everything. I don't recommend that, but R won't complain if you do. Bioconductor might complain about it when you submit to them. But a few general things to remember about the code in this R directory. Any R code you put here will be evaluated when the package is built, not when it is loaded into R by the user. So when someone types library, name of your package, and that package is loaded, that's not when any of this R code is evaluated. All of this R code is evaluated when the package is built, or rather, when it's turned into a binary and installed. So that means that you don't want to do things like try to just have a startup message just by typing print something. That won't work. There are specific ways to do that if you want to. All of the R code here will be evaluated in an environment that will become the namespace of the package, not the global environment. So when you're working with R typically, you're used to just working in the global environment, having access to whatever variables are in this global environment. The code evaluated, any of the code in this R subdirectory will not be evaluated in that global environment. It will be evaluated in its own environment, and that environment will then become the namespace of that package. And what I mean by that is, so for example, so every package will create its own namespace. That's just an environment for all of the objects it contains. So for example, if I want to see everything that exists in the devtools namespace, I can use ls, look at the package devtools. I guess I need to attach it. Let's look at matrix. I can look at the package matrix namespace, see what all objects are in there. Not all of these will actually be exported, so I'm not able to access all of these. This is just everything that the matrix package has in its own environment, in its own namespace. So any R code in your R scripts will be evaluated in this separate environment. Any R objects that you assign in this R code will not be visible to the user unless you explicitly export them from the namespace. And we'll talk about how to do that with both, either by writing the namespace by hand or by using Roxygen to automatically generate this. But that means that you can have a bunch of functions. You can have things like little helper functions. So here in this MSExample package, I have some utility functions that are not actually exported to the user. So if you load this MSExample package, you won't get to use locmax1, but the package can use this locmax1 function. So functions and objects are only exported to the user if you actually say that they are. And this should, anything in here should be mostly functions, methods, and class definitions. You should not use code that creates side effects outside of creating new functions or setting new methods. So don't just write a plot function that you think will run when a user loads your package and it will plot something automatically. Don't do that. That's not going to work. And in general, you don't want to mess with the user's global environment. You don't want to do things like read or write files, communicate over the internet, set user options. Your package should behave well and not do any of those things unless the user explicitly calls a function that intends to do those and they know that that's what they're doing. So don't do things that just create side effects or does things without the user knowing what's going on. All code will be evaluated in the order that they appear. So our scripts will just be listed in that folder in alphabetical order. They'll be evaluated in alphabetical order. Usually this doesn't make a huge difference. It doesn't usually matter that much for most, the way that you write most functions, most basic functions. For S4 classes and methods, which we will talk more about later after the break, These do have to be defined in the proper order, so you can't define a methods for a class that doesn't exist yet. So sometimes it does matter the order that that this code is evaluated. And you can control that either by just changing the names of your files so that alphabetical order gets everything correctly, or you can use explicitly a collate field in your description file. So in your description file, you would just add a collate field, and then this would just list all of the R files that you have in your R directory in the exact order that you want them to be evaluated. And that's all or nothing. If you do that, you have to list all of your R scripts in the order that you want. You can't just list the ones you want first or the ones you want last or anything. But that does let you explicitly control the order that these are evaluated. Any quick questions on the R code so far? Okay, so there is the man directory. So this contains all of the manual pages, all of the documentation. So everything that you export to the user needs to be documented in this man subdirectory, including functions, methods, class definitions, even data sets if you have any data sets. Typically these are written as .rd files, which is a format that's based on LaTeX. So if you are already familiar with LaTeX, this format should look fairly familiar to you. You do not need to write them in LaTeX. If you want, you can use this Roxygen2 package. This lets you write your documentation as code comments that's near your functions, and then you run Roxygen2 Roxygenize, which will generate these .rd files, which you should not edit by hand. You should instead edit your code comments and run Roxygenize again whenever you want those updated. So you have a couple choices there. You can either use Roxygen2, or you can write these .rd files by hand. All of the documentation for this MSExample package is written in Roxygen2, and it has .rd files that are generated by Roxygen2, so you can both look at the Roxygen2 comments to see how those work, as well as the output.rd files to see how you would write that up yourself by hand. So yes?
So you're going to show an example?
Yes. Yes, so for example, I have a function called SimSpectra here. It's a function for simulating random mass spectra, and the way that I would document this using Roxygen2 is every Roxygen2 comment that will eventually be turned into some sort of documentation starts with the hashtag octothorpe pound. What do you all call it these days?
It's
I like the pound. I like octothorpe. So you start off with the normal R comment character, and then you follow that by an apostrophe. The apostrophe after it is what tells us that this is a Roxygen2 code comment that will be used for documentation. And so it's pretty simple. You just have the first line here will become the title of the documentation page. You can then write a paragraph that just gives the description of whatever the function happens to be. Then you need to document all of the function arguments. Here I'm going to go ahead and start R. I'll load MSExample, so I can see how this actually looks. So I'm going to use question mark SimSpectra to pull up this help page. So this is what your user will see if they pull up the help page in R. This is the Roxygen2 code comments that produce this. So you can see simulate a mass spectrum. This is the title. The next paragraph is just the description. This usage part will be generated automatically by Roxygen2 just by looking at your actual function definition. And then all of the arguments you need to specify yourself. You need to document all of the arguments in any function that you have, and you can do that just by using this @param. So anything that starts with an at here is some sort of Roxygen2 command. So here you use @param to document the parameters. @return here helps us document whatever is returned by the function. So this @return will become the return value down here. So here I'm just documenting each parameter, @param_n, the name of the parameter, a short description of what that parameter is or should be or is used for. @return, I need to document the return value, what the function actually returns to the user. And then if I want the user to actually have access to this function and be able to use it, I need to export it. And so Roxygen2, when it generates the namespace file, which we'll look at in a moment, it will go through and look at which functions have been exported like this, and it will export those to the user. Your user does not get to actually use your function unless you export it. So that's the documentation for SimSpectra. What that actually produces in terms of these .rd LaTeX-like documentation files looks like this. Let me open it up. So this is what the .rd file looks like. So you would create this using Roxygen2 Roxygenize. So I would just call this function Roxygenize on my package, and it'll go through and generate all of these .rd pages as well as the namespace. You can see that it was generated automatically by Roxygen2. By these comments up at the top, it carefully tells us not to edit them by hand, because whenever you run Roxygen2, it will rewrite it anyway, so don't bother trying. So you can see this is set up like LaTeX, if you're familiar with LaTeX. We have the name, alias, title, usage. We can talk a little bit more about things like that. So the alias here, for example, anything, I can add an alias for essentially whatever name I want here, but the alias means that whenever a user types question mark and something that's an alias, it will pull up this help page. So question mark SimSpectra, it will look for what help page is aliased to SimSpectra, and it will pull up this one. You can add additional aliases if you have multiple things documented in the same place. So this is an S4 method, which we'll talk about this after the break. But you can see it has two aliases here, one for the generic function and one for the S4 method. If you don't know what those are, we'll talk about that after the break. Yes?
So you showed that for the documentation we have that file which has this argument param and then the parameters. So what file was that? Because both of them were the documentation file as download, right?
So the comments these comments that are used to create the documentation, this just lives in the .r files.
Okay,
So you just put this above the function itself.
So this is within the function.
Yeah, so this is the actual R script that assigns this function SimSpectra. All of the actual R code is right here. And the way that you write these Roxygen2 comments is you just put them right above whatever function, whatever you're documenting.
Okay, so and in the markdown file you mentioned that if we need to make any adjustments, we make it here. And
Yes.
it will automatically be synchronized with the other one.
Yes, so if you want to change the documentation and you're using Roxygen, that means you have to edit the documentation here through the Roxygen comments. Any changes you make to the actual .rd files will be completely lost the next time you run Roxygen2. So whenever you run Roxygen2 Roxygenize, it'll generate the documentation files and eliminate any changes that you've happen to have made there. So if you want to update the documentation, it has to be in these code comments if you are using Roxygen2. And that can be nice in some ways. there are ways that it can make writing the documentation a little bit easier. Sometimes it can be a little bit harder. I don't like having to remember to run Roxygen 2 every single time that I want to update my documentation. Again, this is kind of a personal preference thing. If you think, if you like this and think it will make your life easier, please use it. If you don't like it, then you can just write this kind of stuff by hand. So documenting the package itself, so sometimes you need to document things that aren't actually functions that you can document using Roxygen 2. So Roxygen 2, it expects these code comments will appear whatever function or object they happen to be documenting. But say you want to write a general help page for your package. So I want something that I want users to have a help page if they just type question mark. If they just type question mark MSExample. There should be one. So you can see here that I didn't actually create an alias that's just MSExample. What was generated was a help page for MSExample-package. So the way that you would create this, first of all, is since there's no MSExample function, you just document null, which seems a little bit odd, but that's the way that Roxygen 2 does it. So if you want to create either a help page or do manage your namespace, obviously there's no exact functions that directly correspond to that, so you just document null, put all of these code comments above null. So you can see this is my documentation that ends up going in to this help page that you get when you type question mark ms-example or MSExample-package. And I can also see that if I want the user to actually get here, if they just type question mark MSExample, then I should add an alias. And I should add an alias for MSExample. I'm not going to go too in detail about exactly what each of these different doc type name aliases and things are. It doesn't help that the naming scheme here is ever so slightly different than what actually ends up in the .rd documents. You can find more information about that in the R packages textbook that I linked you in this section on documentation, which should also have a link to the Roxygen 2 documentation somewhere. So here, this is also where you would manage your imports, so what functions you are using from other packages. So for example, I'm going to import methods and import graphics, so I have access to all of the functions from methods and graphics. I'm going to import S4 vectors, which is a Bioconductor package, and Prot generics, which is another Bioconductor package, so I have access to everything in those packages. I can also just import specific functions from a package. The reason I might want to do this is certain functions might exist with the same names in multiple packages. So I think I think S4 vectors implements its own version of some functions from stats, which is why I'm importing S4 vectors, but only grabbing the functions I actually need from stats. And this is something that you'll get a warning about either in R command check or when Roxygen 2 is generating this. So whether or not you're using Roxygen 2, you'll eventually get a warning by R command check at the very least, telling you about this. So this is how I'm controlling what functions I'm importing from other packages, and we saw how we export things. So any functions that I want users to have access to, I need to export like that. This is what these particular comments generate in terms of the .rd documentation. The way that we can generate the documentation is just running Roxygen 2 Roxygenize. DevTools document also just runs raw decision IDs for you. I'm not sure if there's a particular advantage of doing it one way over the other. All right, and namespace. So we exported those things. We imported some things from other packages. The namespace is where all of that actually ends up with the instructions for what you're using from other packages and what your package depends on, and what your users will have access to in terms of your own functions from your own package. So the namespace directives use import and export, which define what you're importing from other packages and what the user will have access to. Import just makes all of the functions from another package available to yours. Import from lets you selectively import specific functions. Again, that can be useful if you're using two packages and they both have a function with the same name, then you might want to just import from the particular functions you're using from one of those. Otherwise, you'll get a collision, and you don't want to do that. Exports, so any normal R objects such as functions, you need to export. S3 method, export classes, export methods. These are specific for S3 methods, export classes, and export methods, which we'll talk more about after break. But they have their own ways of exporting them, just using different directives. So what? Yes.
So you mentioned about the confusion between two functions, which might be one package and I am using the same function in my package, in my code.
Mm-hmm.
So is it always the case that when I run to compile, compile that my package, it will give me a warning about this? Because if it does not, then what will be the hierarchy that which overrides the other, and how would I detect that? Because it's impossible to know what function exists in all the other packets.
I'm pretty sure I've gotten a warning every single time that I've done it. Let me try. Actually, yeah.
So basically the question is, if you get it, you know it, but if you don't get it, how do you know that there is no other class? And one function is not overriding the other.
Well, that's what will happen, is one of them will overwrite the other.
Right.
In this particular case, and I'm going to assume it's whichever one shows up last in the namespace, I'm going to assume is what will overwrite the other one. But every time that has happened for me, I've gotten a warning whenever I try to build or install it or check it. I suppose if you're using devtools load all, I don't know if that will give you a warning or anything.
Because if we get a result when the whole package is running, and we don't get any warning, that's a dangerous thing, because I don't know where the result came from, either that function or this function.
Right. So one thing that is always a good practice to do as well, that I should probably do more myself, is just fully specify the name of the function that you're going to use using this. So for example, let's say stats filter. So the stats package has a filter function. So the stats package has this filter function. Dplyr, if you've used Dplyr, also has a filter function that does something totally differently. If I want to use functions from both stats and Dplyr in my package, one way that I can make absolutely sure I'm getting the right one is to just always specify that function like this. So dplyr ::filter when I want that version of filter, stats : filter when I want to use that one. And this is something that I have used a few times myself. I should probably do this more often. But whenever there is a chance for confusion, so for example, one of my packages also has its own version of the filter function. So in the case that I need to use the stats version, I would specify it like this.
Or in other words, like when I'm creating a function name, is there a way that I can put into a database search of all the R functions existing somehow?
All of the R functions?
Exactly, that's the point, right? There's so many of them, and it's hard to know which function exists hidden in one of the other packages.
And next week another package.
Yeah.
Collisions. Alternate packages. So you're.
Right, I'm saying like some online database or something of our package where I can check that if the function name is already like a username when you create an account, it's already taken a set.
Right. So for you would probably have to write your own script that would exhaustively search for that. In terms of when you're writing a function in your own package that might share a name with something else. So suppose I want to write my own filter function. I wouldn't worry too much about that. Obviously, if you know that a common function with the same name exists, like filter, then that's something I would think kind of hard about before doing. But I wouldn't be overly concerned about it because in terms of what the user sees, they will always, so whenever the user loads your package, they will always get a message with any functions that are masked from another package, and the user will always just get whichever one they loaded, whichever package they loaded most recently. So here I just loaded an attached dflyer. I get a warning that filter and lag are masked from stats. So now whenever I use just the filter function without any additional specification, I will get the dflyer version of filter. If I want, I can still access the stats version of filter. But if I just do filter, I'll get the dflyer version, and this is something that eventually users will have to learn to manage, and at the very least they will always get that message. So it's something that is unfortunate, but is kind of expected that eventually there will be some functions that different packages will have the same name of. And when we talk about S4 generics and methods this afternoon, it's one way to at least resolve that a little bit when multiple people want to use a function with the same name, is to use generic functions and methods defined on them. That's not always possible, though, but that's something that we'll talk a little bit more about in the afternoon. And after the break, that's one potential solution to that. Does that answer everything? Perfect. Okay, so the namespace. So we've exported functions, we've imported stuff from other packages, and this tiny, tiny text is what I get when I run Roxygenize on this MSExample package. So I can see I'm importing these packages, I'm importing these specific functions from stats, and then I have a bunch of other things that I'm exporting. In this case, they're mostly S4 methods that, again, we'll talk about this afternoon, but I have a few that are just basic functions, like I'm exporting this SimSpectra function. And again, this is something that if you're using Roxygen 2, you should not edit by hand. You should edit those code comments with the @export, the @import. If you're not using Roxygen 2, you would edit this by hand and create all of this yourself. All right, the data directory. So optionally, an R package can have a data directory. This is where any data that's saved in an R format, such as RData or .rda, using either the save or save RDS functions. This is where that kind of data lives. Typically, this data is not loaded automatically, and you can use the data function to load this kind of data from a particular package. But this is one way of making data somewhat easily accessible in terms of for writing examples, for writing vignettes, making some sort of data set available to your users. Typically, these should be relatively small, and this also is specific to the .rdata or .rda files. If you want to include, say, a CSV or XML file or something, that would be included in a different way. Any data sets that you include like this must also be documented. And they can be documented using Roxygen 2 in a similar way that you document functions, or you could also just write the RD file by hand. I'm not going to go into documenting data right now. Okay, installed files. So you can optionally have an inst directory. This is an optional directory, but any files that are included in this inst directory will be moved to the top level directory where the package, or wherever the package is installed. So for example, there is a function called system.file in R. It takes one of the arguments that you can give to it is package, and you can give it any package name that you have installed. And this system.file will give you the path to where that package is actually installed in your computer. So here is the actual installed version I have of this MSExample package on my computer. I can see it has a few things. It has this R directory with these it's .rdb and .rdx now. I'm guessing that's because recent versions of R byte compile the code. So it has some sort of binary versions of my R code. Has some other kinds of metadata. This is for the documentation, and so forth. But essentially, if I had an inst directory in my original source package, those files would be moved here. And so if you wanted to include something like an example CSV file, XML, an MSExample file, or something like that, something that's not saved as an R data file, you can put it in the inst directory and it will be moved here to this, wherever your package is installed. And then you can figure out where it is programmatically by using this system.file package equals the name of your package. And so that's the typical way that you would gain access to something like an example XML file or something like that. Or also any, say, if your package depends on, say, a Python script or some other interpreted script language that's not compiled. If it's compiled, it belongs in the source directory, but something like a Python script you could also put there. Compile code, this is something, again, we'll come back to tomorrow, but this is where any C, C++, or Fortran compiled code lives. Finally, vignettes. So vignette is some sort of high-level overview walkthrough of your package written either using Sweave or R Markdown. In our examples, we'll be using R Markdown. But this is where the vignette files would live. So if you're using R Markdown, it would be a .rmd document in this vignettes folder. If you're using Sweave, which is a LaTeX version of the same thing, essentially, it's a little bit older, it would be .rnw. Lots of people use R Markdown instead now, so this is where your .rmd R Markdown vignettes would live. MSExample package has an example of vignette. This is wrong. This should be use this. The use this package now controls this use vignette function, but you could use this use vignette to just create this vignette directory and create a basic R Markdown template for you that you can go fill in and to write your vignette. So for MSExample, for example, here I have this vignette. We'll take a bit more of a look later, but it's just this .rmd file in my vignette subdirectory. Unit tests, again, we'll come back to this more later, but any unit tests you have should be in the tests directory. Teststat is one of the more popular packages for this. The way that teststat actually asks you to do this is you have a teststat.r file in your unit test directory that just loads teststat and your package, and then calls test_check on your package. And then all of your actual tests live in a subfolder called teststat within your tests package. And are just named test dash whatever you want. And we'll take more of a look at this later. But this is where all of your unit tests live. Okay, so building a package is what turns the source package into a bundled package. You can build that from either the command line or from R. We've done this already, but I'm going to do it on this MSExample package. Let's see. We go to command line. So I'm in my directory with my source MSExample package, which is in my projects folder. And I'm going to do this from the command line since we've been using devtools so far. I'll show you this instead. So I'm going to do R command build MSExample. this case, I already have a char.gz from the last time I built this, but this will create a new one. You can see it does a few things. It'll check the description. It'll clean up your source directory if you have unnecessary files in there. By default, it will install the package and build the vignettes, and then uninstall the package. It's a little bit confusing, but it needs to have the package installed in some way to build the vignettes, and then it gets rid of it again. So it creates the vignettes, does some additional checks, and then returns this .tar.gz. One common option that I use when I'm developing more quickly is sometimes my vignettes take a while to create. So if I just want to quickly make the package, I can do r-command build, no build vignettes, and you can see that it goes a lot faster because it doesn't have to install the package and build the vignettes. Now I'm going to install it. I can use r-command install to do that. You can also use install.packages from R. But first, before installing it, let's go ahead and take a moment to check it. So r-command check, actually, we're going to go ahead and stop here for a moment. So we're going to take a break for refreshments because it's about that time, and then after we've gone to the bathroom and had some more coffee, we'll come back and we'll go ahead and try checking this package before installing it, see if we have any errors. We'll also try checking the package skeletons, which I know will have some errors, so we can see what those look like. But I'm going to stop for a bit and let you all go get some refreshments. We will come back at, I think, 11. I don't have the schedule in front of me, but let's say 11.